Welcome everyone to the Calculus BC course. We are starting chapter 5 here in the Stewart Calculus textbook. This chapter deals with integration, so it's going to be a bit of review to start the year from the Calculus AB course. And so we're going to go back through integration, review areas and distances, as well as the fundamental theorem of calculus. And so we'll start with areas and distances. So our key ideas in these notes are going to be to do the following: find the area under the curve of a graph using approximation methods, find the true area as a limit of the sums of all of those approximate areas, and then determining distances from velocities as well as other applications. So this should look quite familiar to us. So the way that we started approximating area under the curve was to take our subinterval, so in this case between A and B, so A and B are the endpoints of our domain, and we split that up into some number of partition segments, which we call subintervals, and typically we would make them the same width. So we'd say delta x is going to be the width of each rectangle. So each rectangle would be delta x in width, and we would get it by calculating it that way. We're actually going to start here with a slightly less formal, or slightly more formal version where delta x doesn't actually have to be the same. We'll assume that it is for this case, but note that width between rectangles in each subinterval does not have to be the same. And then we're going to select a sample point from each subinterval. And the way that we selected this in the Calculus AB course was really 4 different ways. So one was using left endpoints, right endpoints, midpoints, and trapezoids. So in this case, we're not going to specify which one we're using. We'll assume that we're using one of those. The picture here is actually using right endpoints, as we can see that the vertices are all connecting with our graph at the right vertex of the rectangles. But again, it could be any of these methods. Doesn't matter which one it is. And then we simply take each rectangle and add up their areas all the way until we get to the nth rectangle, however many finite number of rectangles we have. And that sum would give us our approximation. So for our examples, we're going to really focus on kind of revisiting those particular methods. So we've got a midpoints example here. So you can read through the setup for that problem. So we've got a quadratic function. We are between 4 and 16 along the x-axis. And we want to use 3 subintervals. So we're given quite a bit of information. We'll assume delta x is equal width. So to start, we can sketch a rough graph of our region here. So I'll scoot over a little bit. So it looks like we've got 3 subintervals. So let's note that delta x is going to be 16 minus 4 over 3, which equals 4. So that means we need 4, 8, 12, and 16 to be on our graph. So why don't we put that there? So let me mark this out. So we've got 4, 8, 12, 16. And then our actual graph is going to pass through 0 and 20. And we can get that pretty easily by factoring our quadratic there to get the zeros. So we've got our rough shape here. And again, what we care about in this example is what is happening from 4 to 16. So let's fill in those points there, and we're going to use midpoints. So if we're using midpoints, then I'm going to take the midpoint between each subinterval. So my first subinterval is from 4 to 8, second subinterval from 8 to 12, and then from 12 to 16. So we need to add in our midpoints here, which will be at 6, 10, and 14. And so at those midpoints, that is going to be the height of each one of our rectangles. Okay, and then we would add up those areas. So if we do some quick calculation here, we know that each delta x is 4. And then the height of the function at each point is what we would need to calculate. So this would be f of 6, f of 10, and this one would be, oops, f of 14. So then our area approximation using midpoints would be 4 times f of 6 plus 4 times f of 10 plus 4 times f of 14. And you could calculate that on your own and get your approximation. Now you might wonder, is it an overestimate? Is it an underestimate? It's a little bit unclear. So if we know what the true area was, it would be a little bit easier. And we've got increasing and decreasing behavior of our function. So there are still some questions lingering there. And again, I'll leave it to you to work out what the answer is for that approximate area. You might actually integrate this then to see how close it is to the true value. And midpoint is typically a pretty good approximation comparatively to left or right endpoints. Okay. So for number 2, same type of problem. We're going to use 5 subintervals of equal length, but now we're going to use right endpoints. So we'll use right endpoints. So our subintervals, if we've got 5 on 0 to 10, that tells us delta x is going to equal 2. So we'll go from 0 to 2, 2 to 4, 4 to 6, 6 to 8. And we can construct our rectangles from there. Now, since our function is increasing, we can see that it's going to be an over approximation because every rectangle is above the true curve. So this will be an approximation. And then the area using right endpoints is going to be 2 times, and then we can actually just factor a 2 out of each one of those individual areas. And it'll just be f of 2 plus f of 4 plus f of 6 plus f of 8 plus f of 10 for all 5 of our rectangles. And again, you could calculate that on your own and get the value for it. All right, so now we're going to get a little fancier. And we're going to take the limit of that sum, and we're going to let the number of subintervals approach infinity. So we have an infinite number of subintervals. So the only thing that we've done here is increase the number of subintervals to this infinite value. So it's just going to get bigger and bigger and bigger. And what you're going to see is that as it gets bigger and bigger and bigger, all these little areas that are under or overlapping are going to get filled. And they're going to become the exact areas because those subintervals are going to become so small that they just fill in exactly every single area. Okay, and this is the definition of our definite integral. So this expression, of course, is the integral from a to b of f of x dx. That's an equivalent expression that we defined last year in the Calculus AB course. And we spent a little bit of time kind of working through the limits. They can get quite messy, but then we quickly developed the fundamental theorem, which allows us to evaluate this much faster. And just note below that whether we use right endpoints or left endpoints, the limit is still the same. Right? The limit is still going to equal the same value because it gives you the true area. This would also be true if we did midpoints. So if we had midpoints in our representation here or trapezoids, it would still be the same. So it doesn't matter really which endpoint method we use because we're going to have an infinite number of subintervals, which indicates to us that the delta x is going to approach 0, right? The width is going to shrink down to essentially 0 and account for every possible area portion underneath that curve. I'll just give you some reminders of some summation formulas that we have here that will be useful. Don't expect anything beyond the cube summation formula, but these are going to be useful definitely when evaluating Riemann sums. And note, yes, this is our Riemann sum, named after Bernard Riemann. Okay, so we've got some additional examples here, some true-false, area under with right endpoints, and then velocity as well. So the area under the velocity curve will tell us distance if the area is a positive area above. So note, the curve is telling us velocity versus time, and it's above the axis. This would be distance, because it's always positive, so we're always increasing in one direction. Whereas if I have velocity versus time and I'm above and below the axis, this is going to be displacement. So displacement versus distance. But it's still going to work the same, where we're just finding areas under the curve using some endpoint method. This one doesn't tell us how to do it, so you can do right endpoints, left endpoints. You can decide which way you want to do it. And then a additional example with speedometers. So you can find the completed notes for those examples on the website and kind of briefly discuss that first portion there. So I would finish those examples, check your answers, and if you have questions, don't hesitate to email me.